Hello everyone, I'm Mengxi, and together with my teammates Peng-An Chen and Harrison Hildebrandt, we would like to present our master thesis titled SLACPACK, Frameless Fiber Winding of Deployable Spatial Structures. Our research aimed to develop a frameless filament winding process that utilizes SLAC fibers and multi-robot collaboration to create bespoke deployable spatial structures. Due to the prevalence of geometrically unique forms in architecture, it is important that construction methods remain efficient even when producing different components. Yet, the mass customization of fiber components is ultimately limited by the need of formwork, which interrupts the design-to-fabrication workflow and reduces geometric customizability. Fiber winding in architecture is introducing advanced technologies, such as industrial robots, into construction. Yet, the construction's technological adoption is relatively small. The prefabrication process increases production efficiency and quality by manufacturing everything in a controlled setting, but is limited by increased logistical costs, inefficient shipping configurations, and limited vehicle size. In order to address these limitations, our research first aimed to remove the frames from the winding process. It then explored the potential benefits of a multi-robot system. And lastly, it investigated how the flexibility created by our frameless method could increase the logistical efficiencies of prefabrication. A frame is a component in the winding process that constrains the fiber in its intended shape until it is cured. Anchor points on the frame, as well as the resulting fiber-to-fiber interactions, create the structure. So all that is needed to create a fiber structure is the geometric relationships between anchor points, or nodes as we call them. As long as the fiber and node relationships are locked and secured, it doesn't matter if the structure is in tension or slack, it will retain its overall morphology. We determined that in a multi-robot system, a hybrid material node could be established as a manipulatable object in order to achieve slack winding. This resulting method eliminates the need for a frame by storing completed members in slack on a storage plane. Winding of members is achieved through a node bot and a fiber bot, where fiber is locally secured on the nodes. The ability to alternate between states of tension and slack without losing the geometric relationships of the members allows the finished structure to remain in a collapsed state and then be deployed on-site via tension and on-site curing. These constraints form the basis of our geometry generation logic and are used as the behaviors of an agent-based model that determines the node's locations from a given boundary condition. After the nodes are generated, members between these nodes are generated according to an ascending z-height, valency limitations, structural feedback, and geometric influences. The tensionability of the structure is tested in Kangaroo, and structural analysis is performed in Caramba, including a cross-section optimization. In our dual robotic system, the nodebot manipulates the nodes and fiberbot performs the winding. Nodes and previously wound members are stored untensioned on the winding platform. To prepare the global geometry for fabrication, it is projected onto a 2D plane and analyzed to get the projection lengths and angles. The resulting fabrication process is a coordinated sequence between the fiberbot, the nodebot, and the nodebot ender effector. You can see a sample of the functionalities of the nodebot ender effector here. The specific tasks of the nodebot ender effector are picked and place nodes, adjust the lengths between them, and locally cure the fiber just at the node. This was achieved through the development of a completely custom ender effector. Localized curing, or spot curing as we call it, is achieved by running an electrical current through the carbon fiber so it heats and cures the resin just at the nodes to allow the fiber to go slack without losing its geometric relationships. Here you can see the effect of localized curing. Not only does winding in slack solve a number of collisions and reachability issues, but it allows the completed structure to remain in an untensioned collapse state, improving transportation efficiency. It can then be deployed on-site via tensioning and cured in an expandable autoclave. We tested the system iteratively, beginning with the prototype geometry. It was wound by hand with one robot holding the nodes in position, and deployed with the robot holding the top plate, and cured with the expandable oven. Here is the resulting structure. Then we tested prototype 2. Demonstrator 2 was a demonstrator that tested our entire system, and this video shows off the full process. Its global geometry was generated with the agent-based model. The robot programming was done using the fabrication planning algorithm, and it was fabricated using a dual robot platform and the custom ender effector. During the actual winding, the node bot and the fiber bot works collaboratively to pick up two nodes at each time, winding around them, cure in place with electrical curing, and then dropped off on the storage plane. After this process, the robots will go to the next pair of nodes. The process keeps going until in the end the whole global geometry was wound. As a result, the full network of structure in the slack state was wound. The structure was then deployed with a crane and cured on site. The final demonstrator is shown here. The last prototype was a larger scale piece to demonstrate the potential of the system. The structure was computationally generated using the slack pack method, with areas of higher axial compression getting thicker bundles. The final structure was wounded by hand and deployed, with some final shots of it. Comparing prototype 1, which was done by hand and without an informed global geometry, to prototype 2, which was algorithmically generated and fabricated using the slack pack method. While geometry 2 used 30% more material, it could support over 250% more load before deflection, greatly illustrating the strength of the slack pack method. Furthermore, by comparing prototype 3 to an equivalent structure in steel circular hollow sections, we see significant weight savings for equivalent structural performance. Using multi-robot collaboration, SlackPack leverages the introduction of slack into the winding process, removing the requirement for a frame and extending achievable structure sizes far past the dimensions of the fabrication envelope, which can have direct architectural and construction implications out in the world and even beyond the Earth applications. This research project was realized as a master thesis within the iTech Master of Science program at the University of Stuttgart, led by the ICD and the ITKE. We would like to acknowledge everyone who helped to make this work possible, particularly our tutors Rebecca Estrada and Christoph Dahimeister. Thank you.